more people. Yes.
Would like to tell you when it's 10 to 3, something like this? Or?
No, I'm going to use this.
Oh, okay.
Sorry. Then I'll check at some point. I'm going to talk it. I will poll the audience. Should I keep going?
We can start.
Thank you.
I'm going to do a countdown. You can start.
Thank you, Richard. Hello to everybody. Good afternoon. First, welcome to this first seminar of the second semester of this year at the Astronomy Department of IAG-USP. And we are very glad that this is the first seminar being held in person at our institute, at least for the series, the cycle of seminars, since the beginning of the pandemic in 2020. So thank you all for your participation, for your presence here, physically or via Google Meet, YouTube. And today we have the pleasure of having Dr. Ciriaco Goddi, a new researcher from our own department. And for those who do not know Ciriaco yet, I would like to share a few biographic information about him. He got his PhD in 2005 from Cagliari University in Sardinia, Italy. And since then, he worked as a postdoc researcher at in institutes like Harvard and ESO, as ESO Fellow in Germany. And he was a project scientist of the ERC-funded Black Hole CAM project at the Radboud University in the Netherlands, and as a support scientist in the ALMA Regional Center Dutch Node at Leiden Observatory, also in the Netherlands. Recently, Ciriaco moved to São Paulo after he got a FAPESP Jovem Pesquisador grant to work at the IAG, developing research, especially in astrophysical jets using radio interferometry. Ciriaco, thank you a lot for accepting this invitation. And today he's going to present the seminar, Imaging Black Holes with the Event Horizon Telescope. So, Ciriaco, feel free to start.
Great. Thank you for the kind introduction, Rinaldo. I'm really glad to be here opening this new colloquial season for this year. So, thank you to the organizer for giving me this opportunity. Thank you all for attending here and online. All right. So the story I want to tell you today is mainly the story of these two images that I'm sure all of you, or most of you, will recognize. The one to the left is the first historic image of a black hole. The one at the center of the distant galaxy M87 in the Virgo cluster. It was published 3 years ago. And the one to the right is instead much more recent. We published it about 3 months ago and portrays the black hole at the center of our own Milky Way. And it was actually the prospect of taking this image to the right that motivated the project more than 20 years ago, when a theoretical prediction was made about being able one day to take an image of the black hole shadow at the galactic center. Of course, this story is much more than the story with astronomical images. It is the story of a technological challenge to build a telescope with the size of Earth that could work, observe at high radio frequencies, and to see something that was considered invisible. Okay? But it's also the story of a highly motivated group of scientists, or very crazy ones, depending on the point of view, scientists that at different stages of their career decided to invest everything in a project that was certainly very ambitious, but with an uncertain outcome. Okay, this is my talk outline, perhaps a bit optimistic, but I'll try to cover as much ground as possible in the next 45 minutes. I will start explaining the fundamental concepts that motivated these black hole studies. I will describe the instrument, the Event Horizon Telescope, or EHT. Then I will review the crucial steps that were needed to obtain these images that I just showed you. And then I will briefly summarize the implications of these results and what we learn from them. And if there is any time left, I will talk a bit about the future of the project. We all know that black holes are one of the most fundamental and extreme predictions of Einstein's theory of general relativity. But since their first formulation in 1916 by Carl Schwarzschild, they were not really accepted by the physics community of the time as real astrophysical objects. In fact, a lot of time has passed, and it required a number of experimental confirmations, especially starting from the 60s and the 70s, starting from the discovery of quasars, which appear as very bright objects like stars, from which they got their name, quasi-stellar. But people soon realized that there were no stars because they were at the center of galaxies very far away from us. So these were actually accreting supermassive black holes. And then the discovery of very powerful relativistic jets that can propagate near the velocity, the speed of light, and they can propagate for thousands, sometimes to millions of parsecs from their galactic centers where they're coming from. And only a spinning black hole accreting mass very fastly can act with a high rates can actually explain the enormous energy output that is required to launch them. And then in the 70s, they discovered binary stars, which emit high energy X-rays, where the black hole devours matter from the companion. But perhaps the most compelling evidence of the existence of black holes in the universe was provided by the discovery of gravitational waves, which are ripples in the fabric of space-time produced by the merger of two stellar mass black holes. This discovery was published in 2016 by the IAG-USP collaboration. So all in all, decades of black hole studies led to the discovery of gravitational waves, which have provided wonderful confirmation of general relativity predictions. But even after these breakthrough discoveries, we still lack a direct proof of the existence of an event horizon. And the event horizon is the defining feature of a black hole. So in other words, we still needed to see a black hole, at least its surroundings. And this has always been the mission and the challenge of the Event Horizon Telescope collaboration. So this is the question we started off. What would a black hole look like if one could observe it? So to answer this question, one needs to take into account the line bending in a warped space-time around the black hole. Okay, this is to the right is a visualization from NASA, where the thin bright lines that you see show the path of light rays emitted by material orbiting the black hole. And this material is concentrated in a thin disk, in a super thin disk. But you don't see a thin disk here, right? You see a very warped image of it. And this is due to the extreme gravity around the black hole that alters the path of light rays coming from the disk. And to better understand why the NASA picture looks the way it looks, I would like to use this graphic. Here to the left, we have a black hole. It's surrounded by a thin accretion disk of matter. And here we have the observer. So what happens is that this part of the disk that is closer to observer results in a thin stretch of emission that you see here, what you expect for an edge-on disk. But it is interesting to note that the top of the disk behind the black hole is also visible, regardless of the viewing angle of the observer. And this is because the gravitational field by the black hole bends the light rays here, and this results in this top part of the image with a circular shape. Not only that, but for the same phenomenon, you can see the underside of the disk. So we can see the underneath part here, which is the light rays are bended this way, and this results in the bottom part, the circular part, circular ring on the bottom. Okay. I must point out that the idea of reproducing the appearance of the glowing plasma around the black hole is not new. It was introduced in the first time in '73 by Bardeen, and then the first calculations using Einstein's equations were done by Luminet in '79. It was the first one that calculated the orbit, the path of light rays should have in a warped space-time around a black hole. So now you should understand better why the NASA image looks this way. The top is the back of the disk relative to us, so behind the black hole relative to us. And the bottom is the part underneath the disk. And the part that we see here is basically the disk's image on the front part with respect to us. Okay? And these concentric circles that you see here, they form the photon ring. So this is formed by light rays or photons that orbit the black hole several times before escaping it and reaching us. And inside the ring, the photons, the light rays are trapped. So that's why you see this dark patch at the center, which is the black hole shadow. Okay? And this indicates the presence of the event horizon. Okay? And for Hollywood lovers, of course, this is the image of Gargantua in Interstellar, simulated by Kip Thorne. As you can see, it's very similar to the NASA picture. And this is what you will see if you had a black hole surrounded by an infinitely thin and super hot disk, which emits very, very efficiently. And the black hole is also accreting with a high accretion rate. The reality, however, is a bit different. In fact, more realistic simulations that reproduce closely the conditions observed in MT7 Sgr show a thick accretion flow. Okay? So something that is closer to a toroid, an asymmetric toroid, rather than a thin disk. And this toroid surrounds a black hole, which is a starving black hole. So it has a very low accretion rate. But most importantly, the accretion flow doesn't emit very efficiently. Okay? So we use these RIAF models to describe the emission from the accretion flow, so radiatively inefficient accretion flow models. And this is the reason why we see donuts and not the NASA or the Gargantua picture with our instruments. This is another version of the same simulation where the inclination with respect to the observer changes. I show you that the shadow is pretty circular, but it depends on the spin of the black hole and the inclination with respect to us. So in principle, one could constrain spin and inclination of the black hole from the shape of the shadow image. By the way, these are images that are based on radiative transfer calculations. This one take an input, general relativistic magnetohydrodynamic data, so GRMCD data, and in particular, these were produced using this ray tracing code, BOSS, black hole observation in stationary space-times, and GRMCD code is BAC, black hole accretion code. Both codes were developed in Frankfurt as part of the Black Hole Camp project, which, as Rinaldo pointed out, was funded through the ERC Signature Grant, and I've served as project scientist of this project for the past 7 years. All right, so simulations are very nice, but how can we see the photon ring and the black hole shadow with telescopes? So the first thing to assess in this respect is the size expected of the black hole. Okay? So we take this Schwarzschild solution. We know that the event horizon is proportional to the black hole mass. And if we plug the numbers, we get 3 kilometers for 1 solar mass. Okay? Of course, we are astronomers, so we care more about angular sizes, non-linear sizes.
Ciriaco,
yeah?
Sorry, can we stop some minutes just to adjust the screen size?
Sure.
Because this part is critical.
It's not showing well in...
understanding. Richard will...
Oh, I didn't notice.
Sorry.
Okay, because I have 69, and is he doing
He's
it?
coming to adjust, or he's trying to adjust from there.
Okay, good point.
Just a second.
All right, that's perfect. Thank you.
Richard, thank you. Thank you, Ciriaco.
Thank you. So I was saying, we start from the Schwarzschild solution. The radius, the Schwarzschild radius, which describes the size of the event horizon, is proportional to the black hole mass, so we get 3 kilometers per solar mass. We care about angular size, so we had to consider the distance. And if we include the distance, we get this tiny angle, 0.04 nanoarc seconds per solar mass per 1 kiloparsec distance. So these are tiny, tiny angles, either if you consider stellar mass black holes, which are obviously close, but they are just a few solar masses, or if you consider supermassive black holes, which is sure, they are millions to billion times more massive, but they are also millions to billion times more distant. All right? So they are both generally too small. So it turns out that Sgr star and M87 star are the only exceptions. All right? So M87 is 2,000 times, so M87 star is 2,000 times more distant, but is also 1,500 times more massive. So they are at theta Schwarzschild, so the angular size of the Schwarzschild event horizon is similar. It's 20 microarc seconds and 16 microarc seconds, respectively. Okay? Likely, the photon ring and the shadow size is larger than the event horizon, and this is because of gravitational lensing effect. And precisely, it's a factor of 2.5 larger, which was a great thing because without this lensing, we will not be able to resolve our objects. Okay? So the biggest black holes we know of, at least as seen from Earth, are subtend an angle of 40 microarc seconds and 50 microarc seconds. What does it mean? It means that if we need to observe them with a telescope, we need a telescope with a resolution, angular resolution of 20 microarc seconds, something like that, right? So to put things in perspective, what that means, I take the moon. We all know that it subtends more or less half a degree. Then we take 1/6 of a degree, we have 1 arc minute. 1/6 of an arc minute is 1 arc second. Then we take 1/millionth of that. So we are talking about 20 millionth of an arc second, or if you prefer, 6 billionth of a degree. All right? So, and the analogy I always I like to make is that this is the resolution you will need to take a picture of a donut on the moon from Earth, right? And this is just because the M87 picture just looks like a donut. So there is no optical telescope, there is no technique that can attain this kind of resolution. So we had to come up with a transformational instrument in order to achieve the resolution we needed. All right? So this takes me to the second part of the talk on the instrument, the Event Horizon Telescope. And I would like to start from a simple diffraction limit formula, which gives the angular resolution of a telescope observing at wavelength lambda with a diameter d. Okay? We know that the details we can resolve of a source depend on the wavelength, the observing wavelength, and the size of the telescope. So first question is then, which wavelength should we look at? And it turns out that the radio is the more suitable regime to observe our black holes. And this is because of the main dominating emission mechanism of the plasma surrounding the black hole. So this is a spectral energy distribution for Sgr star. It shows all the emitting mechanisms across the spectrum, from the radio to the gamma rays. I don't want to enter in detail the description of the spectral energy distribution. I just want to notice that the peak falls between the radio and the mid-infrared. This is known as the sub-millimeter bump, okay? And this is due to synchrotron emission. So synchrotron is the dominating mechanism of emission of the plasma orbiting the black hole, okay? So the peak is about 1 terahertz frequency, but we know that the atmosphere, Earth atmosphere, is opaque, right? Here I'm showing a portion of the Earth atmosphere absorption spectrum up to 350 gigahertz. As you see, the transmission diminishes, and then it becomes completely opaque at 1 terahertz. That's why if you want to observe at 1 terahertz, we need to go to space, right? So the best thing that we can do without going to space is to observe at a wavelength of 1 millimeter, which is the Goldilocks wavelength for many respects in this project. So we go back to the diffraction limit formula. If we need an angular resolution of 20 microarc second and 1 millimeter, you can easily calculate that you need a diameter of 10,000 kilometers, all right? So basically, we need a telescope the size of Earth, which is obviously geographically and technologically impossible to build, right? So instead, we use a global network of radio telescopes, so small telescopes spread across the globe, which observe the same source at the same time that's simulating a telescope the size of Earth. Okay? So this network uses this technique called VLBI. It stands for Very Long Baseline Interferometry. And this technique works like this. So you have your cosmic source, will emit radio waves, and this will arrive to a pair of telescopes. These are located in different parts of the globe. There is no real-time connections between the two telescopes. Okay, so they will arrive to the telescope with a tiny delay to one with respect to the other. By tiny delay, I mean something like a millionth of a second, okay? So to measure these tiny delays, we need very accurate atomic clocks. So we use hydrogen masers, which lose 1 second every 100 million years, okay? And the accurate measurement of these delays is very essential in each pair of telescopes because it allows us to synchronize and combine the signals without any real-time connection between the telescopes. So I can do this post facto. In other words, it's like I reproduce the interference pattern of the radio waves that are coming to the two radio telescopes a posteriori, post facto. Okay? So in this technique, each telescope works in pair with another telescope. Okay? And each pair provides some information about the source. So if we take pairs that are far apart, they can detect the sharpest details of the image. And then the orientation is also important because different orientations pick up different details of the source. So if you have enough of these orientations, then you can recover all the sharpest feature in your image. Not only that, we also care about telescopes that have short separations because they are more sensitive to the broad features of the source. Okay? So once we combine all these components, then we can have a good representation of our source we are looking at. Okay? Obviously, to make a perfect image, you will need this. Yeah? Telescopes everywhere with all separations and orientations. But we have only a handful of telescopes scattered across the globe. So this is not possible, but luckily, Earth rotates. And since Earth rotates, it basically changes the orientations of these pairs with respect to the source, as seen by the source. Okay? And that's why this technique is called Earth rotation aperture synthesis. Okay? And the big advantage of this technique is that it can achieve the angular resolution of the largest separation between a pair of telescopes. Okay? Now, some of you might have heard of VLBI before. It was invented at the end of the 50s, so it's not a new technique. And in fact, it's standard at low radio frequency, up to 22 gigahertz, no problem. But you can also routinely use a 50 gigahertz up to 90 gigahertz. The problem is when you want to go at higher frequency, like 200 gigahertz or above. And our worst enemy is the atmosphere. In particular, the water vapor content in the troposphere, which destroys the signal, the radio signal at high frequencies. So this requires to do the observations. We need to do the observations of very high and dry size. Okay? And there are not many places where we can do this kind of observations. The other problem is that, as I said, for this technique to work, we need the minimum number of telescopes, right? But these telescopes are very hard to build, as people here build in Yama know very well, because they require very high surface accuracy. You need a fraction of the wavelength you are observing. So you need probably a micron accuracy, even better, on the surface. And this is very hard if you have to build 10, 15 meters or even larger telescope. Okay? And then you have to put these telescopes in this high size and maintain them there. So all in all, it's quite challenging. Okay? And this has been exactly the challenge of the Event Horizon Telescope, to apply the VLBI technique, which was well established at low frequency on a global scale, a frequency higher than 200 gigahertz. And these frequencies were necessary in order to be able to see the innermost regions, okay, of the plasma surrounding a black hole, at least the biggest that we know of. Okay? This is a summary map. The globe, this is showing the telescope, the sites that are part of the EHT, and they are virtually connected by line. You can see 8 here, but now we have 11, so it's, this network is growing, is expanding, and we hope one day when Yama will be ready, we'll also join the network. Okay? This movie shows some of the antennas that are part of the EHT. You can see that they are located in this remote sites, selected based on their dry climates, as I was saying. And I would like to point out that these were all existing telescopes. So the EHT Collaboration has not built any of them, because that would have required major resources. So what the EHT did was to provide the equipment, the instruments that were necessary to do observations in VLBI mode. And this obviously has required some investment, a considerable technological development, and setting up this network took more than 10 years, okay? And a lot of work and cooperation between different institutes and countries. But anyways, after 10 years, in April 2017, we were finally ready. We had 8 telescopes ready to observe in VLBI mode. So in different teams, we reached all these remote sites to do the observations. And I went to the Atacama Desert to observe with ALMA. And allow me to point out that ALMA is the crucial element in the EHT network. Going back to the challenges of millimeter VLBI, one of the issues is that the dishes are small. Typically, they are 10, 12, 15 meters. And this is related to the problem, I would say. It's very hard to build a large dish with this very high accuracy in the surface. Okay? If we compare to radio dishes, I think you have in Brazil, even in the state of São Paulo, some 32 meters radio dish. We have Greenbank, Effersburg, which are 100 meters in diameter. We even have FAST in China, which is 500 meters. It's a non-steerable dish, but still. At lower frequencies, you can have much bigger dishes, so you have a lot of collecting area that you don't have in the millimeter. On top of that, the receivers perform much more poorly. All this translates in a quest for higher sensitivity. Okay? We need sensitivity to capture the weak signal. And one way to solve this problem is to use existing interferometers with lots of dishes to increase the collecting area. And ALMA includes 66 antennas located in the plateau at 5,000 meters above the sea level in the Chilean Andes. And being in the Atacama Desert obviously enjoys a super dry climate. So all in all, ALMA is the most powerful and sensitive radio telescope ever built. And to all of us that started the project many years ago, it was clear that in order for this to work and to be able to get an image of Sgr A 87, ALMA had to join the network. Okay? The problem is ALMA is not a single dish telescope. ALMA was built to work as an interferometer, not as a single dish in a VLBI array. So we had to turn ALMA into a single dish, and we did this with this project, ALMA Fusion project, that we started in 2013. And this project built a beamformer that can aggregate the entire collecting area of the array into a single very large aperture, a virtual aperture. And this is done summing up, synchronizing all the signals from different antennas. And since we normally phase up to 41 antennas, this corresponds to a virtual dish of 73 meters diameter. This compares with 10, 12, 15 meters of the other dishes. So you can imagine how much we gain with ALMA, and that's why ALMA is the reference station of the array. And if you want to know more about how ALMA works in VLBI, you can read these papers published in PSP. We have actually submitted just one this month, and is describing the performance on the instrument at the higher frequency band. So far, the EHT has worked as observed at 230 gigahertz, and the future is the 345 gigahertz band, that we will gain a lot in terms of resolution and also transparency of the synchrotron emission. If I have time, I will speak about this at the end. Now, the observations were done in April 2017, the first campaign. But during the EHT run, we also coordinated a very complete multi-wavelength campaign with other partners. These are summarized here for Sgr and M87. So this included X-ray satellites like NuStar and Chandra. We had high-energy satellites. We had Magic. We had Fermi. So in the TV-GV regime, we had the VLT covering the near-infrared. We had other instruments covering the low-frequency band. So we have a very good coverage across the full spectrum. And this is very important because it greatly helped to interpret the EHT data. All right, so the question you might ask now, okay, there is this EHT, these antennas, this network collecting all this data, but how do we get an image from the data collected with the EHT observations? Now, there are various steps, and I will try to quickly guide you through the most important ones. First, focusing on data processing, and then to the imaging, okay, of the data. First of all, EHT observations produce large amounts of data, okay, to manage. In 2017, we collected something like 4 petabytes of data. And the last observation this year, we collected over 15 petabytes, okay? It's a huge amount of data, cannot be transferred over the internet, okay? So what we do is we digitize the signals, we copy them onto hard drives, we use 10 terabyte hard drives, and then we literally fill large boxes with these hard drives, and we load them in containers and aircrafts. And with just 5 nights in 2017, we filled up something like half a ton hard drives. Some of them are shown in this picture. These are all hard drives. Okay, so EHT is really big data science. Then we ship these disks to a center that we call a correlation center. We have actually 2. One is at Haystack MIT in Boston. The other one is at the Max Planck Institute in Bonn. Here the data of all the antennas are combined in pairs by the supercomputer called correlator, after synchronizing the signals and basically creating post facto the interference pattern of the two of the radio signal detected at the pairs of the antennas, as I was telling you before. So then the correlated data is passed to is delivered to the calibration teams, where we correct distortions, introducing the astronomical signals by the instrument, by the atmosphere. And finally, once the data is cleaned and ready, fully calibrated, we pass it to the imaging team, where we use specialized software to turn the interferometric measurements into images. Okay. Before going to the imaging process, let me add that unfortunately, millimeter wave BI is very challenging, not only in terms of observation, but also in terms of data calibration. And again, the effect of troposphere reduces the coherence time. So the phases change so quickly that we can't easily sum up the data, integrate the data over a long time series in order to build up signal to noise ratio. So the signal is normally very weak. Then the other problem is that the EHT is very heterogeneous. This is because it's made of telescopes that are all very different. They have different sizes, different sensitivities, different mounts, different slewing times. They are in different size. So everything is different. And calibrating this data with these very different telescopes is really a big challenge. So that's why we had to develop novel data processing pipelines and algorithms. I won't go into details of this because it's fairly technical stuff. I just wanted to point out that one of the 2 data reduction pipelines that we used was developed by my former student in the Netherlands during his PhD, Michael Jansen. So I thought to give a shout out to Michael for the wonderful job that he did during his PhD. All right, so imaging the data. These plots here are showing the so-called UV coverage for about M87 and Sgr. To understand what's displayed here, imagine that this plane is the dish of our virtual telescope. And this plot shows you where we have measurements, okay, in correspondence of those colored points, okay? If you prefer another analogy, if this were a camera, the colored dots will be showing you the only active pixels, okay, which receive signal from the source. So each pair of telescopes, these are indicated with different colors, gives you a measurement or a pixel in this virtual dish. But you must see that it's not a point. There is not one point per color, right? There is this curved line, right, for each pair of telescope. And this is due to Earth rotation, as I mentioned before. This video is showing to the left all the telescopes observing at all times. In the middle, the coverage or the sampling of our virtual parabola, and the reconstructed image to the right. And as you can see, as Earth rotates, the parabola gets filled with these color curves, right? And consequently, we get more information gradually on the source until we can finally make an image of the source. So this video is showing you an image can only be obtained after a full semi-rotation of the Earth. So after a full night of observing. So with this technique, we don't have the power of taking snapshot images. Okay? This is very important and unfortunate. The other thing I wanted to point out is that even after one night of observation, you have relatively few color points in your virtual parabola. So the UV coverage is very sparse. That's the term we use. So in order to reconstruct an image, we need to interpolate between measurements in order to fill in the missing information. And this is a crucial and critical step. So in order to reduce bias in this process, we adopted a multi-stage procedure. Okay? First, we have developed 4 independent algorithms which work in very different ways. They make very different assumptions. And so these 4 algorithms fill in the missing information in different ways. Okay? Not only that, we use these different methods in 4 different teams, each blind to others' work. Okay? And we do this to avoid shared human bias, okay? But also to assess common features in the reconstruction of the image. If 4 different teams that don't speak to each other found the same features, that means that that is probably a real feature. Okay? And finally, we construct a large suite of synthetic data to exercise the imaging algorithms by the different teams. And particularly, we consider 7 different geometrical models. 3 are ring models, and 4 are non-ring models. And these models have properties that are similar to the data we have, okay? The observed data. So the way it works is the following. First, we create synthetic VLBI data that correspond to these models. Then we run this data in the through the imaging pipelines. You get some resulting images, and you compare these resulting images to the ground truth images, which are these ones. These are the starting points. So we know exactly how they should look like, right? Okay, so this survey allowed us to first assess the dependence of our images on our assumptions. And second, and most importantly, allowed to select a set of parameters to use in the imaging pipelines that we can then use to reconstruct the images of our sources, so real data, okay? So using these fiducial parameters, or top set parameters, how we call them in the paper, we found this, we reconciled these 3 images of 87 with 3 different algorithms. I told you that we have 4 algorithms. The 4th actually was created for Sgr. So in 2019, we had only 3, okay? But as you can see, the 3 images look basically the same, which is a good thing. But since we didn't want to be biased against one method versus the other, we took an average of the 3 images, and that's the image that we published, okay? Now, while this procedure resulted in 1 unique image for M87, for Sgr we got thousands. And they all look different in the brightness distribution in the ring, okay? So all these images are compatible with the data. And since we could not choose just 1 image a priori, because they are all compatible, we have adopted an agnostic approach. So we took an average of these thousands of images, and this is the image that we published and you have all seen, okay? So you might ask, why do we get 1 image for M87 and thousands of images for Sgr? Well, this is a consequence of 2 main complications in observing Sgr we compare to M87. First complication, time variability, fast time variability. Sgr is 1,500 times smaller, has a smaller mass than M87, so has a smaller radius, Schwarzschild radius than M87. That means that photons go 1,500 times faster. Okay, how fast? Well, we can use this, this formula. We can take the dynamical time scale at the ISCO, the innermost stable circular orbit. This has a very easy analytic expression, and it depends only on the mass. If you put the mass of M87, you get 60 days. If you put Sgr mass, you get 30 minutes. If the black hole is spinning, it's even shorter, up to a factor of 10. So we get dynamical times as low as 4 minutes. So you can realize that while we are observing the source, it's changing under our nose. And remember, images are made with data acquired during an entire night. Okay? So this is a time interval where the source could have changed up to 100 times. That's why the image of Sgr star is less circular and more fuzzy, less symmetric than M87, because you are looking at a variable source. So we needed to measure this time variability. This is a light curve that we measure with ALMA. Showcases how the millimeter emission from Sgr star varies as a function of time during the course of the same night. These are hours. So this is one night of observation. So the flux density varies quite a bit. We have similar light curves in the near-infrared and X-rays. Besides these measurements, we had to account for this variability in our data analysis and modeling. Okay? So we had to develop new algorithms and perform more extensive testing when compared to M87. And this partly explains why we published this image 3 years later after Sgr star, something I didn't say. Both images are made of data acquired on the same days, right, in 2017. So it took us 5 years to get to the Sgr star image. Okay? That's not all. There is another complication. Which is the complication? Well, Sgr star, we are looking at Sgr star through the disk of the galaxy. So through clouds of ionized gas. Okay? So we have scattering. And the scattering is very insidious and has two components. There is the diffractive component, which has the effect of blurring your image, okay, as you see in the central panel. The left panel is the ground truth image, and the one in the middle is the diffractive blurring. But even worse, there is a refractive component, which adds substructure to your source. And this is terrible because it's stochastic and time variable. So I don't know if you can see it from here, but introduce a lot of substructure. So basically, this hides all details within the ring. We cannot see it. And that's why the image of Sgr star is much fuzzier and blurrier than the one in M87. Scattering is responsible for hiding crucial details in the ring of Sgr star, all right? And this is a picture I like to show because I think illustrates best the difference in imaging Sgr star versus M87. Now, scattering effects can be thought as blurring a subject behind the window on a rainy day. And then dynamical effects can be represented by a dog chasing its tail. Yeah, that's Sgr star. M87 is our nice setter sitting there. It's very easy to take a picture. It doesn't move. Okay? That's what we are dealing with. Now, a last point on the image of Sgr star I want to make is that it has this peculiar structure, right? Let's see if it starts over. With 3 bright spots. Okay, you might have noticed that. In fact, we realized that we could cluster these thousands images into 4 categories based on similar visual features. Okay? 3 of the clusters contain a ring-like feature showing a peak at a different position angle, here, here, and here. And then there was also this 4th cluster that contained images that did not appear ring-like. Okay? So what we did was first to take an average of images in each cluster, and then we imaged the 4 resulting images, okay? And that's the final image that we published. The average was weighted by the percentage of their appearance, okay? And this is the reason why the image has these 3 peaks here, because it's an average of this image, and this image. And the bright spot has a different position angle, okay? Now, I say that we have no ring clusters, but this is a very small percentage of images, only 2%, because otherwise it would imply that we don't really know that this is a black hole, because there is no, if it's not a ring, how can it be a black hole shadow? But it's only 2%, and we cannot, let's say, rule out these 2% of images from the data. But one thing that we can say for sure, the vast majority of the images contain a ring of exactly the same size, 50 millionths of an arcsecond, which is the angular size predicted by general relativity for a black hole with a mass of 4 million solar masses at a kiloparsec distance. Okay? So after years of work on the data and testing, counter-testing, we can conclude with high confidence, okay, that what we are seeing is indeed the shadow of the black hole at the galactic center, which has been always the objective of the Event Horizon Telescope. So actually, I didn't start counting the time. So I realized that I've spoken for quite long on the first 3 parts. But by now, you must have realized that EHT is a project based on data acquisition and processing. So I really want you to take that point home. It's not just 2 pictures that we make very easily. I suppose many of you might be more interested on the scientific interpretation and implication of these EHT images. So if I can have maybe 5, hopefully less than 10 minutes more, I can try to cover some of these aspects, okay? I'll try to be fast. So what we can say now is that black holes are not just abstract concepts or a solution to an equation. They are a laboratory that we can use to study accretion process in black holes, formation of relativistic jets, but most importantly, we can observe them with telescopes, okay, to understand black hole physics, but also to understand gravity in general, okay? Now, in our collaboration, we do extensive modeling to interpret our observations. In order to build realistic simulations of a black hole, we need 4 key ingredients. The core of the theoretical work is provided by numerical simulations which use general relativistic magneto-hydrodynamic codes. I mentioned this before, GR MHD codes. We have several that we do cross-comparison between this, across these codes. They determine the physical conditions of the plasma accreting onto the black hole. Okay? These require an input to set the black hole space-time. This can be general relativity, but it can be also an alternative. It can be any space-time in principle. So these codes that we use, they can work also in alternatives to GR. Okay? Of course, they require also an input to black hole properties, the spin of the black hole, and other properties of the plasma, like the accretion state. You have this model, SANE, MAD, and so forth. Now, the third ingredient we use is relative transfer models. So we use ray tracing codes to model the electromagnetic emission from this plasma. And through these ray tracing codes, we created these images that show the appearance, you know, of the accreting plasma around a supermassive black hole. Last step, we need to link the theoretical models with real observations. So from the purpose, we construct synthetic images using actual observing parameters of our instrument, using as ground truth the images from the GRMHD and GRRT models. Okay? Now, after all this process, we can then compare the models to the actual EHT data and images. Okay? Now, using this recipe, we create a library of over 60,000 different simulated images for M87. Each image uses slightly different parameters, different masses, orientations, magnetic field configurations, electron temperature, and so forth. Okay? So this is why they all appear different. Okay? Some have more structure, some have different asymmetries, and so forth. But they all have one characteristic in common. They are bright ring with a dark patch at the center, which is the signature of the black hole shadow of the event horizon. Okay? For Sgr, we produce an even larger library. And this was necessary to account for those problems I mentioned before, right? Those complications, like time variability. We produce something like 500,000 images at 230 gigahertz, but then we produce also images at other frequencies, 86 gigahertz and 2.2 microns. So we basically compare this something like 2 million images to 11 different observational constraints. These are coming, 6 are coming from the EHT, and 5 are coming from different instruments. Okay? So doing this exercise, you can rule out a large number of models. We don't end up with just one model. We say, that's it. This is Sgr. But we have what we call the best bet models. And these are strongly magnetized. They have positive spin. And they have accretion rates that are between 10 to the minus 8 and 10 to the minus 9 solar masses per year. OK? Now, besides these black hole accretion models, I don't want to go more in detail of that. You can read the paper 5 of Sgr if you're interested. Perhaps the most interesting application or interesting opportunity is to use EHT images to test GR. Okay? So the most relevant question at this point is whether what we see is consistent with GR, okay, with general relativity. Qualitatively, we can already say yes, because we see this bright ring okay, around the dark patch at the center. This is consistent with the emission from the photon ring around its shadow, the black hole shadow, right? As I introduced you before. But obviously, we can do a more quantitative analysis and extract parameters from our measurements and see how they compare with the theoretical predictions. So from the image, we can measure the size, the shape, and the asymmetry. Okay? Now, the size in GR depends on the mass and the distance, okay? At least for a Schwarzschild black hole. If the black hole is spinning, the size can be as small as 7.5%. So it can shrink for a maximally spinning black hole. Okay? The shape. The shape is a perfect circle for a Schwarzschild black hole. If you have a spinning black hole, then you get a dent, and there is a departure from circularity. It's a few percent effect. Also, if GR is not correct, if you consider different space-time, the shape changes. Unfortunately, the two effects are coupled. And then you can use the asymmetry, actually, to infer an inclination of the black hole. You might have noticed that M87 has a bright emission in the south and dimmer emission in the north. And this we explained with GR effect called Doppler beaming or Doppler boosting. So plasma that is coming towards us boosts the emission, and plasma that is going away from us produces dimmer emission. Okay? So this is telling us that M87 plasma is moving clockwise. So we can get handle on orientation. For Sgr, unfortunately, we cannot do that because we have three peaks here, which I explained to you before. They are just a result of a spurious effect of the imaging process. So we can't constrain the inclination of Sgr with the image, unfortunately. Okay? Now, anyways, we can compute the size and the shape of the black hole shadow. We can fit, for example, the peak of the brightness distribution in the ring. Since we cannot measure circularity with an accuracy larger than 10%, we cannot estimate the spin from the images, unfortunately. So in the following, I will focus only on the size mass measurement. So we measure the size and we get the mass, okay? Not the spin. We can constrain the spin. Now, for M87, there are two independent measurements of the mass. One comes from gas dynamics. This is observing the alpha line with the HST, Hubble. So this is a disk that is something like 40 parsec in the nucleus. And then there is another estimate from stellar velocity dispersions within 20 parsec from the nucleus. And both use Newton's law of gravity because, of course, we are very far from the nucleus. So there are no general relativistic effects. And as you can see, there is a factor of 2 discrepancy. Now, we can go back to the Schwarzschild radius formula I showed you before. We consider the angular size with the distance. If we assume a distance of 16.8 megaparsec, measured independently before, we get a mass of 6.5 billion solar masses for the M87 black hole. And this compares very well with the stellar velocity dispersion estimate. Okay? And just for you to understand the depth and the beauty of this result, I'm plotting here the different scales. So with EHT, we are probing scales of 40 light hours. Okay? So this is the time that the photon takes to go through the event horizon. Okay? So our estimate is based on gravitational field exerted on photons very close to the event horizon. And the stars orbiting in a disk, they are about 20 parsec away from the nucleus. So we are looking at, we are probing a very far field regime. But if the theory of gravity is correct, it should work for the near field, strong field regime, and the far field, weak field regime. And this is beautiful confirmation of GR, at least if you assume that the stellar velocity dispersion mass is the correct one. Okay? For Sgr, we could do a much better, stringent test of GR, simply because we had a much more precise prior on the mass and the distance, thanks to this study that has followed the orbits of 30 stars within 10 arc seconds from the galaxy center. And these stars appear to be moving very fast, up to 1,000 kilometers per second, around the dark point. And just using Keplerian laws, we can determine a mass of the dark object in 4 million solar masses. Okay? These orbits have been measured with near-infrared telescopes, the VLT and Keck. So these are 8-10 meters class telescopes supported by adaptive optics. In particular, the orbits of stars within 1 arc seconds, these are the so-called S stars, in particular S2, provided the most precise estimate of Sgr star mass and distance so far. Okay? And these are actually the last published values of the mass and the distance for Keck and VLTI. We can use them to calculate the angular size, the gravitational angular size, simply m over d. And these are the results, Keck and VLT. As you see, there is a 7% difference between the two. Well, these are their measurements, so we don't discuss those. We use both as priors. So here I summarize very quickly the GR test that we have done in this paper 6 that we published in May. So we use m over d to get theta g, okay? And then we use that to predict the shadow diameter of Schwarzschild black hole, okay? Non-spinning black hole, which has a simple analytic formula. And then we compare this with the measured ring, you know, from our images. And we introduce this parameter, delta, which is a fractional deviation from Schwarzschild. So if we find that delta is 0, that's a perfect match with the Schwarzschild black hole. So we can say, well, this is a Schwarzschild black hole with this mass and this distance. If delta is different from 0, well, it can be a spinning black hole. So if you have a spinning black hole, I told you that the size of the shadow can be as 7.5% maximum smaller, okay? So if we measure a delta between minus 0.075 and 0, then what we are seeing is consistent with Kerr metric, okay? So it's consistent with GR. If we see a value that is outside, that's an indication that there is a deviation from GR, okay? And these are our results. They're shown in this plot here. This is the sigma parameter. The different curves are indicating the sizes of the ring measured using different imaging algorithms, and also using different models, image models, to calibrate the ring diameter versus the shadow diameter. There's a subtle theoretical concept there that I will skip, but it's all in the paper, or maybe I have another slide if people are curious. And what is important here is this purple shadow band here. This is the range of validity of Kerr, because you can have a spinning black hole, so there is a 7.5% validity of Kerr. So 0 is Schwarzschild, and then as you move to the left, the spin increases, okay? And the conclusion of this analysis is that the images, observed image size is within 10% consistent with Kerr, okay? Which is great. So the conclusion of this is that the EHT images of Sgr star M87 are consistent with a rotating Kerr black hole as predicted by GR. So we are consistent with GR within 10%. Obviously, we would like to make this statement within 1% accuracy. And also, we would like to measure the shape of the shadow with 1% accuracy. In that case, we will be also able to estimate the spin of the black hole. But we are not there yet. And this is part of future work. We have collected data in 3 campaigns after 2017. We have added telescopes. We are continuously adding telescopes. We are going to observe at higher frequency. So we'll have a 50% higher resolution. So the future images will have a much better quality and consistency. So I'll stop here and I'll take questions. Thank you. I think I went a bit long.
Thank you, Ciriaco, for this incredible talk. Scientifically very interesting, and also the visual, the plots are incredible, didactic.
Thank you.
Everybody learn a lot watching this. So let's open for questions. So let's start with Rodrigo.
Thank you. Thank you, Ciriaco. I'm glad that with the first talk, with the first talk in person after 2 years and a half, this was such a great quality talk, you know.
Thank you.
So my question is, what is the reality of the 3 blobs in the Sagittarius A star image? Like you seem to point out that 98% of the mock images in the image library had this feature. What is the reality of the 3 blobs?
Okay, so we basically do not constrain the brightness distribution around the ring. So what we really constrain is the fact that there is a ring, and the ring has a size of 50 million arc seconds. Okay. So the presence of these blobs is now indicating real physical features that we can interpret. I heard people that are not part of the EHT describing this as hotspots, because they say, well, Sgr star is a very dynamical black hole. You can have hotspots going around the black hole every 30 minutes, so we are simply seeing these hotspots in different times. But this image is not, these images that I'm showing that are all different, these are not just time frames in a series. No, they are made with the full amount of data acquired during the same night. So if you had something that was transient, like a hotspot, okay, and you average an image over 10 hours, you shouldn't see a hotspot. You will see something continuous. So it's simply a spurious effect of this difficulties in imaging, and we absolutely do not associate any physical interpretation to these hotspots. Okay, so it's a spurious effect. And this is why we can't constrain the inclination of the black hole.
Nice talk, thank you. My question is about what is next, and in particular, if we want to observe stellar black holes, what is the time scale for that? Or say, does we require telescopes, radio telescopes in space, for example?
No. So the EHT will always observe AGN, so supermassive black holes. Stellar mass black holes are simply too small. It doesn't matter if you go to space. One thing that I didn't have time to go through is that, is this working? Wait a second. Actually, the talk was all about the image of Sgr star M87, but with DHT we observe normally in each campaign a dozen AGN. Okay, so these are either not enough massive or too distant to be able to resolve the shadow of the black hole, but we can see the launching region of the AGN jet. This is a beautiful result that we published with the same PhD student I mentioned before, Mikkel Jansen, in Nature Astronomy. And we basically resolved the launching region of the relativistic jet. So this one is a very close radio galaxy, only 3.8 megaparsec, but its black hole is only 55 million solar masses. So it's not massive enough for us to resolve the shadow, but we can do jet physics to understand the launching mechanism of this relativistic jet, which has been an open question in the last 50 years. So we are doing a lot of AGN science. Even going to space, we might be able to see the shadow of this object because we will need the frequency around 1 terahertz. So if you put satellites in space and you have, for example, 3 satellites which have similar orbits but moving at slightly different velocities, you basically change their locations very efficiently and you get a very nice coverage. Okay, so this will be a very nice target for space VLBI. Yes.
Okay, thank you.
Hi, Ciriaco. Thanks for the presentation.
Yeah.
What I wanted to ask is that you said the emission we're seeing is synchrotron, right? Coming from some sort of RIAF engine, some relative inefficiency engine. Does this mean we can't really interpret the images we're seeing as actually an accretion disk, but more of like a blob around the black hole? My question would be, is it you can still take information from like the temperature distribution for the particles around that region by using these models? Or are they kind of distorted and blurred with the scattering effects that you mentioned?
Well, obviously, I went really fast in the part of modeling. We produce millions of models where you change all these physical parameters, including the electron temperature versus the ion temperatures. And what we try to do is to rule out as many models as possible, but we don't have, with this data, we can constrain the model so precisely that you end up saying, okay, the ions have this temperature, the electron have this temperature, and so forth. You can give a range of models which are compatible. That could describe would result in this, but we cannot be, on the astrophysical model, we are not so constraining, you know, of the physical conditions.
Right. Is this a matter of like, if we add more telescopes, it would constrain the images better? Or something like, if we put some radio telescopes on the moon, maybe it would constrain better, the images a little bit better, these models?
Well, I'm not sure I can give an answer to that. We will increase the resolution, which will allow you to get a better handle on the structure of the ring, which will be very important for GR testing. But on the plasma physics, I think what will be more important than that will be to observe multiple frequencies, okay, with the same resolution, and then having a combination of different wavelengths will be more discriminating for the plasma physics. But again, we have no handle on the plasma physics just using this observation. So we rely on multi-wavelength observations. So we combine all the constraints.
Okay, thank you.
Betty?
Oh,
Open
it's coming from
your microphone. You
there
can
is
make
no
your
microphone.
question.
No.
Hi, Ciriaco. Hello. Here is Elizabeth Alpino speaking. So very nice talk. Thanks a lot for this wonderful talk. I have two questions, a scientific one and a technical question, if I may. The scientific one regards the polarization measurements performed by Event Horizon in the surroundings of M87. And those measurements, of course, they could infer about the magnetic field structure aligned with the jet, which is nice. But on the other hand, the polarization degree was very small, surprisingly small. And this points probably a high depolarization rate in the surroundings, right? That might be correlated with the presence of turbulence and probably driven by MRI. So what are the prospects for, new measurements on polarization for these two sources? And what about the results of polarization measurements made for Sagittarius A? Can you comment on this?
Yeah, so you are completely right about, I'm showing no, it's not showing anymore. Okay. I was showing the image that we got in the paper in 2021 on the polarization. So this, nobody's seen it anyway. So I'm the only one seeing it, but it doesn't matter. I cannot do anything, right? Or
I think if you just...
no, but I think I can comment.
Oh, okay.
Or is there something that I can do to show it? Or?
Yes, I think if you share screen.
Oh, I'm not... Anyways, maybe I can just comment because it's not showing your entire screen.
Richard?
So the fractional polarization that we got in the M87 ring was much lower than we expected from, from synchrotron emission on horizon scale. So now it's showing maybe. Anyways, it's showing like this. So this is partly due to what you mentioned, but another effect is Faraday rotation. So in order to be able to get the intrinsic linear polarization, one important application that we will be able to use in the future is to have observations at different frequency bands. So the image that we published of M87 in polarization and total intensity, also for Sgr star, was based on frequencies that were in total. The frequency span was 2 gigahertz. Okay. In 2018, so 1 year later, we acquired observations which span the frequency range from 2016 to 2030 gigahertz. Okay. So there we have enough frequency span that we can try to measure the Faraday rotation. So we can measure the VPA, the electric vector polarization angle, as a function of frequency. And then we can also measure a Faraday rotation. So we can assess if this lower fractional polarization is due to Faraday rotation. Okay.
Right. That's nice.
And for Sgr star, well, that's the next result. So I can't really comment on that. But that will be the next result that you will see from the EHT.
Right. Yeah, I thought that you could, make some spoiler, but it's okay.
So, but with the 2 frequency bands, we will be able to handle to interpret the polarization measurement better. Yeah.
Right. That's great. I will be looking forward for it. Yeah. So my second question, if I may, it's more technical in the sense that, okay, so it's nice to know that you are very welcome to IAG, and probably you will be very connected to Llama project, right? And you know that there were, within this collaboration, there has been a lot of efforts in order to be able to enter in the Event Horizon collaboration once the Llama telescope is operating, and with providing the VLBI instrument to allow for doing VLBI and participating VLBI operations, and eventually get involved into the Event Horizon telescope collaboration. So can you comment on this? What is going to be your involvement on Llama, and if there are plans for this, for boosting this part of the project, and what would be, the improvement by adding a new telescope to the Event Horizon?
Yeah, well, for sure, I'm really interested in being part of the Llama project to push the VLBI side of it. It was part of the reason why I wanted to join the project here, to join the institute. And Llama will be very important because it provides an intermediate baseline to ALMA. So the EHT is this wonderful network which is made of telescopes which have very large separations, because we need the angular resolution as explained. So if we have a 10,000 kilometer separation, then you have a telescope with the resolution of the size of Earth. But then it doesn't tell you all the story. Simply having high resolution, sure, you can make an image high resolution, but then you are missing all the details on the intermediate and large scales. So the other baselines that we have are very short. So we are talking about hundreds of meters, up to 2 kilometers, which is ALMA apex. Llama is 180 kilometers from ALMA. So this is a range that we don't have covered. And having this intermediate baseline will be very useful to try to image the launching region of the jet, for example, in M87, because we will get a little bit of information on these intermediate scales. Also, ALMA is very overly subscribed. So it's not that we will have ALMA all the time observing. So having a baseline in the same region, even without ALMA, still allows us to do observations with a similar UV coverage. So the location of Llama is very important. The future of apex is uncertain, as far as I can tell, as I know. So also we could do triangulations between ALMA, apex, and Llama. You can even try to observe with long baseline ALMA, Llama. So there are many interesting applications of observations Viyama in VLBI mode. So I'm really looking forward to the telescope so we can start some testing.
Great. Yeah. So see you around. And again, thank you so much for.
Yeah, thank you for your questions.
You are welcome. See you around.
See you.
So I would like to thank Ciriaco again and invite everyone who has a question to ask him after we are offline. In a few minutes. Unfortunately, we don't have a coffee break,
Yeah,
but
I
we
know.
can just chat here a little bit for those
Sure.
who have questions. So thank you again, Ciriaco.
Thank you.
And let's finish the broadcast.
Oh.
Thank you, Richard.